Hello and welcome to the second video in my series of answers to Brian Mullin's claims of problems with landing planes on airfields. Just to make things even more complicated than they have to be, I've chosen to shorten out my videos a little bit, so that means that this video here will also deal with the first video that Brian Mullin made. Alright, so the thing is that Brian Mullin claimed that he has a hard time living with the fact that a space shuttle is able to land on an airfield. Now he talks a lot about the velocity that the Earth is spinning or revolving with, because it's really spinning. It seems like a very fast spin the Earth is doing, and 1700 kilometers per hour is indeed fast. That's faster than the speed of light. But think about it. The Earth takes a whole 24 hours to revolve around itself. Imagine sitting and revolving a Pilates ball or a basketball in one revolution per day. That is really slow. So because the Earth is so big, the surface speed is very high, but the revolution itself is fairly slow. Alright, so the thing is that the reason why an air shuttle or space shuttle really don't have any problems with landing on Earth, on an airfield on Earth, is that there is something called geostationary orbit. Now I can illustrate it very simply just by drawing the surface of the Earth. And then we have an antenna here looking at this satellite up here. That is orbiting in a geostationary orbit. Sorry for my bad spelling or lack thereof. What does that indeed mean? That means that this antenna getting signals from this satellite up here will always get signals from that satellite, because if you take a perpendicular position, then the position of the satellite will always be on the same spot. Now that means that if an air shuttle, a space shuttle, let's do that instead. Space shuttle wanted to land on an airfield over here, and it needed an approach somewhat like this in order to get there. Then the shuttle could place itself up here in a geostationary orbit, and then just tilt the nose down through the atmosphere in order to get where it wants to get. Now this is not rocket science, but it's not easy either. It takes a lot of calculations in order to get the right trajectory, but it can be done. So the idea that the rockets sort of have to, the space shuttle sort of have to guesstimating how to get to that airfield, that's simply not correct. It can be calculated, and since space shuttles actually have landed on airfields, it seems reasonable to suggest that they can. Alright, so that's one thing. The second problem Brian, or Mr. Mullin, has with this space shuttle thing is that he has a little trouble with the notion that if you have a space shuttle out in space, and then they can use these little nozzles to spray out material of some sort in order to move the space shuttle, nudge the space shuttle around. Because as he says, well, you're spraying mass out into empty space. So how can that generate force? And I must admit, it really puzzles me that a structural engineer who most likely have taken classical mechanics and statics in his courses don't remember the notion of impulse, momentum, and most importantly the conservation of momentum. So let's state, if we have a particle P1 with this momentum, that is M1 V1. If we have a particle number 2 with this momentum, that is, lo and behold, M2 V2. So the conservation of momentum says that the momentum has to be conserved. So that means that total momentum must be P1 plus P2, and that is equal to M1 V1 plus M2 V2. That means that if I know the velocity, two velocities, and one mass, I can find the other velocity. Now, this of course means that we have to be in a situation where the momentum is conserved, and that is not always the case. But if we are in outer space and no other forces is doing work or influencing the object in the masses we're talking about, then the momentum will be conserved. Now we can also have this on Earth. If you have two ice skaters standing on a lake and you assume that there's really no friction between the ice and the skates, then you have a situation where the upwards and downward forces cancel each other out. That is the force of gravity pulling the person down, and the force of the ice pushing the persons up. So if they are standing next to each other and one pushes the other, then the momentum will be conserved, and depending on the speed of the push from the one person and the masses of them, then they will gain some speed, both of them. The other person will gain some speed. We know what the speed of the first person will be. Alright, so let's take an example in outer space, because that's what we are talking about. Let's take Fred. So Fred is a happy little guy floating around in outer space with a big basketball in his one hand. Alright, so Fred has a little jet package here on his back, and he has his space shuttle here. It's far away. Alright, so for all intents and purposes we can say that there's no external force working on Fred at this moment. So let's say that the mass of Fred is 80 kilograms. Now I have never weighed a basketball before, but let's say it's a fairly heavy basketball. And that is B-ball. Let's say that's around 5 kilogram mass. Alright, so what does Fred do? Fred wants to think that it would be really cool to see how far he can throw this ball away. That might be. But Fred has to realize that in his jet package he has only enough fuel to get into his space shuttle from where he is. Now of course, if he gets closer to the space shuttle, that's not a problem. But if he gets further away, then that will be a problem, and poor Fred will never get home. But he hasn't considered this, so he just thinks, oh, I want to throw this ball.